if assigned seats by me are a better idea. I'll tell ya.
Flippy, I will start crying. You have a quiz on Friday. He's your favorite. Look, who am I? Sarah.
All right, here we go. 7-2. Here we go. All right. So, direction of the reversible reaction. So, which way is it going to proceed? Okay. In a reversible chemical reaction that has reached equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. When the rate of the forward reaction is greater than the reverse, the reaction is not at equilibrium. The products are being made faster than the reactants, and therefore the products are gaining. The net gain in the amount of products will occur when the reaction, until the reaction reaches equilibrium. At equilibrium, the amounts of both the reactants and the products will remain constant, but they're not necessarily equal. We saw that yesterday with throwing paper wads. Okay? You may have more on one side or the other. The same is true when the rate of the reaction to the reverse reaction is greater than the forward. The reactants are being made faster than the products. There's a net gain in the amount of the reactants. Okay? So here we have this reaction where we're making ammonia. It is at 500 Kelvin. What happens to the rates of the forward and reverse reaction if some NH3 is added? So if we add this in, which way is that going to go? Right now, the rates are equal. We're now going to be adding in more paper balls, I guess, on this side. Yep, it's going to go to the left then. So if you add this in, it's going to shift it this direction. Does that make sense?
So the bigger arrow would be on the bottom? Or like
Yes. Yep, it would be this direction.
So if you add more, then it's not equilibrium?
Nope, it won't be at equilibrium anymore.
Does it go back?
It'll eventually get there. Yep, it'll be there. It'll get there. But initially, it's going to be forming more of this stuff. If we take some of this stuff away, then it's going to go this direction to make more of that stuff until that equilibrium is reestablished. So the rates of the forward reaction, that's this direction, will go down. So this is reduced. And the rates of the reverse reaction going this direction will be increased. All right. In a previously evacuated flask, we have now 0.4 moles of A and 0.45 moles of B, and they're allowed to come to equilibrium. At equilibrium, we have 0.15 moles of C. They want us to sketch the curves on here. So again, we're going to do an ice table.
Yeah. I love ice. Oh, but there's no room to put it. Oh,
This needs to be a 2B here. Sorry.
This group is pretty like blank. I think I'm fine with it.
At least you don't have any issues with self-esteem there.
No, but I mean, if you met this gym class, you'd understand. I mean, they're kind of.
Who's in it? List the names.
All right, here we go. So moles of A is 0.4. Moles of B is 0.5. That 4 didn't turn out very nice. And do we have any C initially? No, so 0. At equilibrium, we end up with 0.15 moles of this, which means that we had to generate 0.15. That's our change. So this guy over here, what's he going to have in his change?
No, point two.
0.15.
Minus 0.
Minus
Oh.
0.15.
And the same for the B?
No, it's minus 0.30.
Okay.
This is just embarrassing.
So this ends up being 0.2 and this ends up being 0.25. That making sense? Anybody not see where I got that data from? Anything that doesn't make sense there? All right, so let's start plotting this guy. Initially for A, and again, guys, can you try to keep it down over there? For A, I'm going to do that as a solid line here. So initially A was at 0.4. It is going to go down to 0.25. So that ends up being right here. So I'm going to take that. And it's going to level off here. All right, B started out here. I'm going to do that as little dots. So B started out here. B is going to end up at 0.2, which is down here. And it'll be leveled off there. So let me try to get this guy. There we go. So that's my B. My C would have started out at 0. And I'll do it as a bigger dashed line. It's going to start out at 0 and go up to here. Oops, I need to make those bigger. Sorry. There. Can you see the difference between A, B, and C then? Does that make sense? I wish I could do this in multicolors. It's not being friendly to me. So, all right, y'all got that? That makes sense? Everybody happy with that? All right. The next one is very important, okay? This is the reaction quotient and the equilibrium constant, all right? And the way these work is some reactions will reach equilibrium when there are more products, while other reactions reach more equilibrium while there's fewer products. The reaction quotient describes the relative concentrations at any time. Okay? So at any time, you can use Q. So Q describes at any point in time. So they say at this time, this is how much we had. K is only at equilibrium. So do you see the difference between K and Q?
Yeah.
All right. We can do, there's a bunch of different Ks. And if you look on your sheet, the one that has all of the formulas on it, they have KC, which we're going to talk about today. They have KP, which we're going to talk about today. C stands for concentration. P stands for pressure. They also have Ka, which deals with acids. That's next unit, along with Kb, which deals with bases. Again, next unit. And KW, which deals with water, we cover that in the next unit. But these are written out here for the next two if you need them like on a test or AP exam or anything like that. Okay, so how do we write them? The way we do that is this little letter here is your coefficient. And this is going to be the concentration or the pressure, whichever one it is. Okay. Now, there's certain things that we don't put in these expressions. Okay. So when we are writing these, if it is a solid, if it is a liquid, we do not include it. Although we do include aqueous things. Okay. So if the liquid is aqueous, we include it. Writing a reaction quotient or an equilibrium constant for a system, you use either the concentrations and label it Q or K. It's Q if you don't know that it's at equilibrium. It's K if you do. Okay? But they're written the same way. Okay? So Q would be the concentrations at a particular given time. K would be the concentrations at equilibrium. Miss Nickel is at home, so she's having to remote in. All right. So here, all of these things are aqueous, so they would end up being included in the expression. Are the concentrations whatever values? Are you listening to me? Are the concentrations whatever values these would end up being? Would these be at equilibrium or not? And how do you know? What does this mean? What does the K mean?
That means it is.
Yes. So these would be at equilibrium. They are raised. The power is whatever coefficient was in the balanced equation. Your products go on top. That's these two things. Your reactants go on the bottom.
How do you know it's at equal?
Because it's K. If it's K, it's at equilibrium.
So if it's Q,
It may be. So if you calculate, K and it's equal to Q, then you're at equilibrium. If your K is greater than Q, then it's going to shift this direction. And the way you remember that is you always write your K first, and then you write your Q. And whatever direction your greater than or less than symbol is, that points to which way the reaction is going to run. So if K is greater than Q, it's going to form more products. If you write these in alphabetical order, this trick will work every time for you. Every time. If you don't, then you have to logic your way through, and it takes you a lot of time. So if Q is greater than K, then it's going to form more reactants.
so how would we find out K?
You would calculate it. They would give you concentrations here, and you would calculate it.
That's how you find out Q.
If you're figuring out Q, yeah. It just depends on what data they've given you.
Okay, so
Sometimes,
equilibrium constant, then it's K.
Yep.
Okay.
And
anything else is
reaction quotient is Q.
Okay.
Reaction quotient.
Okay.
Q is reaction quotient. That's hard to say. All right. You can convert between KP and KC. You don't have to on the AP exam, but you may need this at some point in college. So we just mention it in case you keep your notes for college. All right. If they ask you to write the expression, the equilibrium constant expression, they do not want a calculation. Don't do more than what they ask for. They don't care how smart you are. They just want you to answer the questions. Okay? So keep that in mind. They know that every kid taking AP Chem is smart, or else you wouldn't have taken the class. So you don't have to prove that to them. Answer the question that they ask. Don't piss them off and answer the wrong question. Okay? Fair enough?
Plug the numbers into the formula.
There's going to be a couple numbers, but there won't be all of them. So if we're looking for the equilibrium constant expression for this, that's going to be, we're going to call it KC because they didn't say pressure or concentration. So I'm going to do concentration because it goes faster. So I'm going to start.
Did I do it right? I didn't do it. We can do the answer.
I'm going to start with my products because they go on top. So I'm going to put those in square brackets. Remember, square brackets mean molarity. So the concentration of the CO2 raised to the third power, I got that from the coefficient. Yes, ma'am.
Wouldn't you have to do pressure with this gas?
That's what I saw on the other.
Yeah, I think you're right.
I swear I had it.
See, you guys are smarter than me.
You brought this up? Oh, the gray one?
Yep, you're right. See, I told you guys you're smarter than me. All right, so we will change it. We'll do it the right way. So this is going to be KP. Okay, so I'm going to do the pressure of CO2 raised to the third power. And I'm going to do the pressure of H2O raised to the fourth power. I need to divide that. These are all gases, so they're all going to get included.
Wait, are these in parentheses or brackets?
These are parentheses because we're doing pressure now. And this is going to be over the pressure of C3H8. That doesn't get raised to a power because there's no coefficient here. And then times the pressure of O2 raised to the fifth power. And that's it. Drop your pencil, walk away. They just asked for the expression. Do not give them any more than they asked for. Okay?
What do you mean by giving them more than they ask?
If they would have given you more values in here, like you start with, C3H8 and the pressure is blah, blah, blah. And the pressure, the initial pressure or the equilibrium pressure of oxygen is blah, blah, blah. If they give you that data on there, but they're not asking for the calculation, they're just asking for the expression, write the expression and don't do any more. Don't try to prove how smart you are. Again, they already know. All right, you good? Let's see if I can get this one right for y'all. All right, so we're writing a balance the equation for the reaction quotient. Okay, so we've got decomposition of solid calcium carbonate. So that's going to be CaCO3, and that's a solid. And it's going to produce solid CaO plus CO2 gas. So balance this guy. It's already balanced. Then write the reaction quotient. So this is going to be gas. So Q P is equal to what? It's going to be equal to.
You don't do the solids, right?
Exactly. So it is just the CO2, the pressure of CO2, and we don't need to raise it to anything either. Muy bien. Very good.
Okay, so when it gives us these numbers like the kilojoules and the H constant, we don't need to do anything with that because all it asking for is the expression, correct? Okay. Yes. Thank you, Libby.
So the Q is still the same equation as the K, right?
Yep, exact same. It's just whether you're at equilibrium or not.
So if we were to have, let's say, a solid on the reactant side, no, if we were to have gas on like the reactant side,
Mhm.
only like solids on the.
That would be 1 over.
All right. That's
And it happens once in a while. Like if this was looking at the reverse reaction of this, it would be 1 over. All right, that's it. That's all I got for you today. Work on your homework. Do tomorrow.